Okay, now we're going to look at objective 3 of our three-phase transformer connections, which is the Y delta connection. And again, the Y delta connection is just 3 single-phase transformers where one set of windings, the H windings in this case, are all connected together to form a Y primary, and the X windings are all connected together to form a delta secondary. Because our secondary is connected in delta, the transformers must be matched using the rules for paralleling transformers. Really, whenever we have a delta connection on the primary or the secondary, we have to use matched transformers. If my connection was a Y-Y connection, it's still recommended to use matched transformers, but it isn't crucial to do it. But any connection with a delta, primary or secondary, needs to use matched transformers. And of course, we need to follow the rules for Y on the primary part of the system, the rules for delta on the secondary. This is probably the easiest way to see the Y delta three-phase transformer connection we have, with the 3 H windings connected in Y on the primary and the 3 X windings connected together in delta on the secondary. And one thing to note from this drawing is note how I have labeled the beginning and the end of each winding in the delta connection. The start of the first X winding is labeled A for X1, small a for X2, big B for X1 of the second X winding, small b for the end of it, big C for the start of the third X winding, small c for the end of the third X winding. And this will help us to see, when I go to the next slide, how we go the end of the A phase winding is connected to the start of the B phase winding. The end of the B phase winding is connected to the start of the C phase winding. The end of the C phase winding is connected back to the start of the A phase winding. That's a delta connection, and it'll help us to see how we make that connection in the next slide. This slide is the best way to show how we are taking 3 single-phase transformers and connecting them to give us a Y primary and a delta secondary. You'll see on the Y primary, on the 3 H windings, we have connected from our supply. We have connected a line to the start of each H winding. Line A is connected to the start of A phase winding. Line B is connected to the start of the B transformer winding. Line C is connected to the start of the C transformer H winding. And then the end of those 3 windings are all connected together to the neutral of our supply. So we have a line connected to the start of each winding. The end of all 3 windings are connected together to form a Y primary. On the secondary, we need to connect the 3 X windings as a delta connection. And again, like I had said last slide, the way to do it is to connect line A to the start of the A X winding. The end of that A X winding gets connected to the start of the B winding, where line B is. The end of the B phase winding gets connected to the start of line C phase winding, so it gets connected to the X1 of the C X winding, and the end of the CX winding gets connected back to the start of the A phase winding. So we go end to beginning, end to beginning, end to beginning. That gives us a delta on the secondary. Now, if we have a certain rating for the 3 transformers that we connect together to give us this 3-phase connection, we can calculate some values for the overall transformer. If we are using 3 150 kVA single-phase transformers to make this 3-phase connection, the total VA of this 3-phase connection using 3 150 kVA transformers will be 450 kVA. The primary phase voltage, if our primary is connected to a supply where the line voltage is 4160, the rule for Y is that phase voltage is line voltage divided by root 3. So 4160 divided by root 3 will give us a phase voltage of 2401, right around 2400 volts. Rated primary phase current. In order to do that, I can take the phase VA and divide it by the phase voltage. If I take 150 kVA and divide it by 2401.8 volts as the phase voltage, I will get a current that is 62.5 amps. And if that is the phase current on the Y primary, the line current on the primary is going to be exactly the same value. In Y, line current and phase current are the same value. So our line current will be 62.5 amps as well. The secondary phase voltage. In order to figure out our voltage, we always have to work our voltages from the generator or from my supply out to my load using the ratio that we have. And we have to remember that that ratio always takes place phase on the primary to phase on the secondary. And this is where it's really important to see how that ratio works. If I was just to take 4160 and divide it by 5, I would get 832 volts. And that is not what our phase voltage on the secondary is. I have to take the phase voltage on the primary and use this ratio to find phase voltage on the secondary. So the primary phase voltage is 2401 volts, and that number divided by 5 will give me a secondary phase voltage of 480 volts. 2401 divided by 5 is 480 volts. So that's the phase voltage on the secondary. If I want to know what the line voltage is, I simply use the rules for delta. If the phase voltage is 480, phase voltage will equal line voltage, so the line voltage will be 480 as well. The rated phase current for the secondary would be the phase VA divided by the phase voltage. So 150 kVA divided by 480 volts should give me a phase current of 312.5 amps. And then to find the rated line current in delta, line current is phase current times root 3. 312.5 amps times root 3 will give me a line current of 541.3 amps. So when we have a rating for our transformers, for our 3 single-phase transformers, we can find rated values for the 3-phase transformer connection that we're making. Now we're going to add a load to this bank and find some values using a connected load. Now we have a load connected to this 3-phase bank. The bank is rated for 450 kVA, but we are connecting a 400 kVA balanced load on the secondary of this connection. And we can find some currents and voltages for this system if we like. What is the primary phase and line current? Again, the load on the secondary, whatever load we connect on the secondary, is reflected on the primary. Whenever we say the secondary has a load of 400 kVA, because primary VA equals secondary VA, the primary will reflect a load of 400 kVA as well. And it is like having that load connected to our line voltage of 4160 volts. So if I wanted to find the primary phase current, the easiest way, again, is just use our mother of all power formulas. VA total is V line times I line times root 3. We're looking for I line. We know the other values in this formula. So to rearrange this formula, my I line will be my 400 kVA divided by 4160 times root 3. When we do that, we find our primary line current is 55.5 amps. And in a Y, phase current equals line current, so the phase current is also 55.5 amps. Secondary phase and line current. Again, the easiest way to solve this is to use our basic power formula. VA total equals I line times V line times root 3. rearranging this formula, our I line is our VA total divided by V line times root 3. So 400 kVA divided by 480 volts times root 3 will give us a line current of 481.2 amps. And in delta, the phase current is always the line current divided by root 3. So our phase current for this system would be 277.8 amps. That's basically it for three-phase Y delta connection.